In this video, we're going to look at the loop and junction rule for circuits as an introduction to how circuits behave. So this is the first in the series of videos on our circuits, DC circuits, direct current circuits using batteries, wires, light bulbs, those kinds of things. We're going to look at how we diagram these things because we need a way of drawing out our circuits that's not a photorealistic picture of a light bulb. Define a few terms like branches and junctions and current and voltage. And then we're going to look at Kirchhoff's loop and junction rules, which are kind of the fundamental rules of circuit analysis that allow us to think about the voltage and the current that have to do with energy and charge. So the first real definition that we need to think about is what we call electric current. Current gets the symbol capital I usually in our DC circuits. Sometimes you'll see a lowercase I that's usually reserved for alternating current, like the stuff that you get when you plug into the wall at your house. But the basic idea is that there is a flow of charge, is what we usually say. Technically, what is happening inside of a metal is that there's a flow of electrons, right? If you think about your model of a metal that you probably learned in chemistry, there's this sort of lattice or grid of positive charge, and then there's sort of a sea of electrons that are free to move. That's why they're such good conductors, right? That's why metals are good conductors. And so with that information, we talk about electric current as being the amount of charge that travels past a certain point in a given amount of time. And that's what this picture on the side is. If you were to put your finger at a spot and say, I'm watching right there, and I'm going to count how much charge goes by in a given amount of time. This is measured in coulombs per second, which is called an ampere, named after someone by the name of Ampere. Usually you see it written as either and said as amp, AMP, capital A, lowercase m, lowercase p, or just a capital A as the unit of amps. Again, ampere is used less often these days than just amp. Okay, and so that is the basic definition of current flow. Now, the reality is, and there's a couple of confounding factors here. The reality is, of course, electrons are the thing that do the flowing. That's the thing that can move. But that's not exactly what we say. Okay, so when it comes to schematics, we generally use this set of diagrams. We don't always put an X through the light bulb there. Sometimes we just use a circle. But a battery is a series of long and short lines, the long representing positive. This battery situation actually shows two battery cells stacked together to make a battery pack. Sometimes we'll use one, sometimes we'll use two. It doesn't really matter, but the key thing is that the long side is the positive side of the battery and the short side is the negative. A switch is just showing something that can open and close. The lines are wires, and although we've drawn them in these nice square corners, I would say that there are three wires in this picture, the one connecting the battery to the bulb, the one connecting the bulb to the switch, and the one connecting the switch to the battery. We've just made everything nice and square because it makes for prettier and simpler pictures. If you were to just draw them all squiggly, it's hard to keep track of, which you will see if you are in class and are building circuits, that trying to follow the wires can sometimes really be hard. So that's that. We need two things to make a circuit work. We need a voltage source, an energy source, essentially, which we also sometimes call an EMF. We'll talk more about that later, which is a source of energy for the circuit. We need a continuous conducting path, someplace for the current, the charge, to flow through, from the high voltage, the positive, to the low voltage, the negative, and then you need stuff in between, right? But really all you need is a conducting path and a voltage source. If part of that conducting path is a light bulb, then you get to see lights turn on. Maybe it's just a wire and you don't actually see the current flow. This is a classic example, and if you're in class, I would say take a couple of wires, take a battery, take a light bulb, and try to make it light up. The basic structure of the light bulbs that we're going to use, if you're using the simulation, they just have two connection points where current goes in and out of the light bulb. But if you're looking at a physical light bulb, generally the structure of a little incandescent light bulb is you have a glass globe or shape that is evacuated. Either there's a vacuum in it or there's a neutral inert gas in there. There's a filament, something that glows when it gets hot, and when current flows through, it'll heat up. And then that is connected to the ribbed or threaded side, which allows it to screw into a holder. And the other part is connected to the base. And there's an insulator. Sometimes it's kind of brown or black plastic, usually. Occasionally it's other colors, but those are the most common ones. Stuff kind of like in that color scheme separating out the two pieces of metal, and so current has to flow in a particular way. Right? Speaking of current, the direction of current flow by convention is that it flows out of the positive and into the negative. We imagine that positive charge is moving. This is actually not what's happening. Electrons are actually leaving the negative terminal of the battery and coming back to the positive terminal of the battery. This is Ben Franklin's fault and his contemporaries, because they did not know about subatomic particles at the time when they picked positive and negative for the various signs of charge in electricity. And so they picked wrong. They just picked the opposite. The thing that they called positive is what we call protons. And right, had we flipped everything around, it probably would have made more sense to call what we now call electrons positively charged, because they're the ones that are free to move. But the end result is that the direction we call current flow is actually the opposite direction that the electrons are moving. So when we talk about a battery and we think about like what's going on in it, we tend to color code things. We call the battery with its high or red side and its low or blue side, for kind of like hot and cold kind of analogy, high energy, low energy. The battery does work to push charge around. That's what it does. It comes into the battery with low potential energy, and then it gives it high energy. It's almost like lifting it up and then letting it slide down a ramp. The charge is already there. It's in every wire, every circuit element. It's just being pushed around by the battery, right? If you close the switch, and then the charge can flow from high back to low. Without it, they're stuck. This is a toy that is kind of a funny one, and I don't have an animated picture of this, but you can always look up one of these. Basically what it does is it lifts these little penguins up the step, and then they slide down the ramp, and then it does it over and over again. This is kind of like a circuit. The thing that lifts them up is like the battery, and then the rest of the circuit, the wires and the light bulbs, are like the place where it kind of coasts down, transferring its energy from this electric potential energy that we get up at the top down to no energy at the bottom. It's turned it into, in this case, kinetic energy, motion. But in the case of a circuit, you might turn it into light and heat energy from a light bulb. So this leads us to a couple other definitions. We talk about branches in a circuit, and a branch is a continuous conducting path between junctions. And a branch is special because the current is the same everywhere. And the circuit we've looked at so far only has one branch. The current can flow along one path, out of the battery, through the switch and bulb, and back. That is it. There's only one branch. The current everywhere on that branch has to be the same, like water flowing through a pipe. Unless there's a leak, which doesn't really happen in circuits, then the current is the same everywhere. A junction, though, is where three or more branches come together. It's kind of like an intersection, if you want to use a, cars and people moving on roads kind of analogy. A junction in pipes is another analogy you can use, but you're not all plumbers, so that probably doesn't make a lot of sense to you. But if I look at this circuit, it has two junctions, two places where three or more branches come together. And there are three branches because there are three different places for current to flow. Current can flow through this battery branch, right, from the bottom to the top of the circuit. It could flow through the bulb labeled L for long, more on that in a minute, and through the bulb labeled R separately. Each of those could be a different amount of current because they are on a different branch, and they all come from these two junctions. The other thing we want to talk about is a resistor, and resistors are a big general catch-all term. And basically, it's any circuit element that resists the flow of current. And that is basically everything you put into a circuit. The ideal battery has no resistance. That's actually a lie. And the ideal wire has no resistance. And that's actually a lie, because there's no such thing as an ideal wire unless it's a superconductor. But generally, the way we draw circuits is we imagine that batteries and wires have no resistance and that the individual things you add into a circuit have resistance. This is a good approximation when you have a large amount of resistance in your individual elements and small resistance in your battery and your wires. And we will get into to some examples of where that's not entirely accurate as we go, but that's the basic idea. We'll talk a little bit more about resistance and how it relates to current and voltage as we go on. But this leads us to Kirchhoff's laws, the junction rule and the loop rule. The junction rule is all about conservation of charge, and the loop rule is about conservation of energy. So the junction rule is all about measuring current. And current, which is a measure of how much charge flows per second, is something that you have to measure kind of in line. You have to put it into the circuit and let the charge flow through the ammeter. Well, if we look at this circuit, there is one branch, right? There's only one conducting path for current to flow through. And so there's only one possible current value. Whether you measure the current at A1 or A2, you're going to measure the same current. You can't have more water flowing through A1 than A2 if those were pipes. Yes, the resistor gives it a complex path, but if a gallon of water goes in one side of that resistor, a gallon of water has to come out. A liter of water in one side, a liter of water out if these were pipes. In the same way, if 1 coulomb of charge flows out of the battery, a coulomb of charge has to flow into the battery. There's nowhere else for it to go. So current is the same everywhere on a branch. That is the fundamental idea behind the junction rule. You can't get rid of charge, you can't create it or destroy it. It has to be there. And so how can you get different currents? Well, for that you need another branch, right? Here we now have A1, which is measuring the current coming out of the battery, and A2, which is measuring the current coming through that resistor over on the right. But then there's another resistor, another path for current to flow. So the number of branches is the number of possible currents. You can have an arbitrarily large number of branches, and you could have an arbitrarily large number of currents in your circuit. Current can only change at junctions, because that's where, if you imagine water or traffic flowing into and out of an intersection, that's where you could change paths. It does not change when passing through batteries or resistors. Again, 1 coulomb in, 1 coulomb out. It's stuck. So the junction rule analogy is this, right? If there's 3 cars coming into this intersection and 2 go straight, then 1 goes left. Or if 1 goes left, then 2 go straight. Right? The total number of cars entering the intersection must be the same number of cars exiting the intersection. They can't just appear or disappear. Right? Cars in equals cars out. And so this is due to the well-known conservation of cars law. The current rule, or the junction rule, is the same thing. Current flowing into a junction equals current flowing out of a junction. So I in equals I out, and this is due to conservation of charge, because you cannot just simply destroy an electron or create an electron out of thin air. Right? I1 in, I2 and 3 out. So in this particular junction, I1 equals I2 plus I3. That is the junction rule. So let's take a look at a circuit and see if we can get some numbers here. There are 0 junctions in this single branch circuit. At the various labeled points, the dots, what current will there be? Well, if there's 3 amps leaving the battery going around, then there must be 3 amps over here and 3 amps down here. The current could not be created or destroyed because charge could not be created or destroyed. What about this one? Well, here we've got 2 junctions, 3 branches. Now we have 7 amps going into this junction on the right and 2 amps going to the left, which means there are 5 amps left to go around the other way. And then as we go around the circuit back to this other junction, there's 2 amps coming in from one direction, 5 amps coming in from the other, leading to 7 amps there. And this current, the last current we found, has to be 7 amps because it's on the same branch as where we already measured 7 amps on the other side of the battery. Here we go, a little bit more complicated. 4 junctions this time. Number of branches, 6. You may not see all of them, but there's 1 where the battery is, 1 where there's this light bulb there. Let me grab my laser pointer. We've got this branch here with the battery. We have this branch with a light bulb. And we have this branch with no circuit elements on it, but it's connecting. Then we have this branch with a light bulb, and this branch with a light bulb, and finally this branch with nothing on it. So all of those can be different currents. And so we know that if there are 2 amps, 1 plus 1, coming out of this junction up in the upper right-hand corner, there must be 2 amps going in. And then if there are 2 amps coming out of that junction above the battery and 4 going to the right, that means there must have been a total of 6 running through the battery heading into that junction. So here's an example. How many coulombs of charge pass through point P in 1 minute? Well, for that, we first need to figure out the current. Right? There's 10 amps going into the junction, 4 and 3, and some other amount coming out. The current at point P is 3 amps, which is defined as 3 coulombs per second. And if you multiply that by 60 seconds, that will give you 180 coulombs of charge passed through that point. How many electrons is this? Well, one electron is 1.6 times 10 to the negative 19 coulombs. And that means we get 1.1 times 10 to the 21 electrons. So a coulomb of charge has a lot of charged particles in it. That's something we learned before. And therefore, an amp, which is a coulomb per second, is actually a fair amount of current. We usually will not be dealing with whole amps of current in our circuits that we build at home. So we got the junction rule. Now it's time for the loop rule. The loop rule is about energy conservation for circuits. Energy is measured in this case, is measured in volts. It's volts are joules per coulomb. A joule is our unit of energy, and each coulomb of charge that passes by can carry so many joules of energy. And that's what your battery voltage tells you, right? If you have a 9-volt battery, that means every coulomb of charge that flows through it carries 9 volts or 9 joules, of energy. A 1.5-volt battery, which is what your standard, AAA, AA, C, D cell, the round batteries that are very common in devices, they are all pretty much 1.5 volts if they are standard alkaline batteries. Sometimes they're a little bit different if they're lithium-ion batteries, but you get the idea. And so how does this work? Well, the battery gives the charge some voltage or some energy. It gains energy as it passes through the battery. The battery is like that stair-stepping mechanism that lifts it up in the air like an elevator, like a hoist, something like that. And it loses energy, the charges lose energy, or really transform it into light and heat as they give it to the various resistors. Right? So we think of these as voltage gains and voltage drops. The battery gives you a voltage gain. Each of the resistive elements, whether it be a light bulb or something else, drops voltage. And the voltage is the change in potential energy per coulomb. And this is much easier than trying to think about absolute changes in energy, because for that we need to know how many total charges there are, and it gets a little complicated. So in order to fully talk about this, we talk about what we call a loop. A loop is any continuous conducting path around the circuit. We usually start and end at the battery because that makes it simpler for us, but you don't have to. We're going to do that for our circuits right now because we're going to follow the direction of current, and that'll make our life easy. And the loop rule, or the voltage rule, says that as you add up all the voltage changes, gains and drops around a loop, it should sum to 0. Basically, this says the total amount of energy in the circuit cannot change. So you gain energy and you drop energy. So if a light bulb or a resistor uses energy, it had to have come from the battery. It can't come from some other source. So here's an application. If I have a 12-volt battery, and I have measured the voltage across 2 of my resistors, the drops, I can say, well, I have a plus 12, a gain, as I walk around the loop, kind of using that language. Then I drop 6 volts, then I drop 2 volts, and then I drop some other number of volts to get down to 0, and so that last one has to be 4 volts. So let's go a little bit further. How many loops do we have here? There are 2 main loops, right? There's the big outer loop, and then there's the inner loop. Technically, there's a third loop you could draw that doesn't involve the battery, but we don't know how to do that yet, so we're just going to use these 2. You'll notice I've drawn this 4 volts in a circle around R3. That's how we measure voltage. Voltage is measured across things from one side to the other, so we draw this little extra branch around it showing that we're measuring the voltage from one side to the other. If you actually stick a voltmeter inline in the circuit, the current stops flowing and it's a big mess. So, what are the voltage drops across resistor 1 and resistor 2? Well, we have a 9-volt gain across the battery. We have some drop across R1 and a drop of 4 across R3. So we get 5 volts. 4 plus 5 is 9. And then if you go around the inner loop, you have plus 9 volts minus 5. That means the inner branch has to be 4 volts as well. So the loop and junction rule analogy, right? Charges are like skiers on the mountain in this case. They gain energy going up and they lose it as they come back down. That is the idea behind current and voltage, right? Voltage changes, they gain and lose energy. We don't gain or lose skiers, but the skiers gain and lose energy, right? So the charge is still there. We're just changing the amount of energy it has. So last example here for us. How many branches are in this circuit? 3. How many loops? 2. Right? We've got a junction at the top and the bottom. And what are the currents and voltages? Well, resistor 2 has a voltage of 3 volts, and resistor 1 has a current of 4 amps. Right? 3 volts, 4 amps. So those are the given quantities. And then we can say, well, if there are 6 amps going in to this junction at the top and 4 going down, that means R2 and R3 must each have 2 amps because they're on the same branch. And then we can go ahead and do currents. There's 12 volts for resistor 1 because the loop that includes resistor 1 and just the battery, it's gain 12, drop 12. For resistor 3, we gain 12, we drop 3, and we have 9 volts left. All right, so that's it. Lots here, right? You may want to go back and watch little pieces of it, but I thought I would put it all together. This is kind of our fundamental understanding of the loop and junction rule, current, voltage, how to draw circuits, etc. I'm also going to post a video of how to use the circuit construction kit and measure voltage and current. I will also try to put one together for doing it live in person, so you can look at that as well, but I'll need to get access to a camera and some equipment, so that may take me a little bit longer to post.